Hi, my name is Mark Pothecary and I'm the US Product Manager for Malvern's Size Exclusion Chromatography products. Now, in this video today, what I want to do is give you a bit of a demonstration of our latest advanced SEC system, OMNISEC. And we're going to do that from the perspective of making some measurements of some proteins and protein characterization. So what I want to do is give you a bit of an introduction to the product, what it is and what it does, and then talk about its different components, the different features and what they have to offer, and then we actually have some protein samples made up, so we're going to set up a sequence, run some samples, and then analyze them afterwards and see what kind of information it can give us. So to start with the product then, OMNISEC, as I said, is a complete advanced SEC system, and you can see here it's made up of two modules. So the module on the left is OMNISEC Resolve. Now that's our degasser, pump, autosampler, and column oven. So that's the chromatography side of things. The module on the right is OMNISEC Reveal, and this is our detector module. So this contains multiple detectors, including refractive index, UV vis, light scattering, and intrinsic viscosity. And it contains those in a single integrated compartment. So I think the best way to go through the system and to discuss it piece by piece is to just follow the mobile phase as it runs through the system. So we'll start on the left on OMNISEC Resolve and follow the mobile phase and the samples as it goes through from component to component. So you can see on the top we've got two bottles, the mobile phase supply and of course the waste bottle. And then there are three lines moving from these into the system. These are the supply and waste lines. So the green line supplies the mobile phase, while the clear line supplies the autosampler. The yellow line then is the waste line going to the waste bottle. So these lines go into the system at the top here, and of course the first place they go is into the pump compartment. Now this compartment includes the degasser and the pump. So we start in the top left with the degasser, which is a low volume degasser. It's just a couple of milliliters in volume, 4 in fact. And what's great about that is it just makes changing between different mobile phases so easily. Such a small volume can be purged really very quickly just with an automatic prime, and it means you can switch between different mobile phases, different buffers, for instance, different salt solutions very, very quickly. So if you're looking to switch between applications very rapidly and do different applications, then this makes that a lot easier. From the degasser supply, or from the degasser, we move on to the pump. The pump is an isocratic size exclusion chromatography pump with low pulsation to improve your baselines, and back seal washing to prevent any wear in the seal. So the mobile phase actually flows through the back channels of the pump to continually wash through any salts that might precipitate there, prevent any crystal buildup, and generally reduce seal wear and extend the life of the instrument. From there, we go to a purge valve and then to a filter, which just collects any debris that might be released from the pump over time. So the mobile phase from there works down into the autosampler compartment, down here. Now, the autosampler can make injections from vials or, in fact, from 96-well plates as well. So if that's, for instance, your standard format in the lab that you work in, then you could just drop a 96-well plate straight in there and start making measurements without having to move the samples around. The whole thing is temperature controlled, so you can protect your samples from aggregation, for instance, by keeping them cool at, say, 4 degrees. It can actually heat samples as well to up to 60 degrees, but from a protein perspective, the most interesting thing is, or the most useful thing, is to be able to keep them cool. And of course, prevent samples aggregating, let's say overnight while they're waiting in the sample sequence. Now the autosampler can make injections up to a couple of hundred microliters and down to as low as 5 microliters or even below. In fact, below 100 microliters, it can make injections with no waste whatsoever. So if you're looking to make injections of, say, 5, 10, 20 microliters, and you don't want to use any excess sample whatsoever, you can use it in zero waste mode, and then it'll be extremely frugal with the samples that it injects, which makes it excellent for if you've only got small amounts of sample. So from the autosampler, our samples in the mobile phase work their way up to the columns. And columns are housed in the column oven, which is obviously a temperature-controlled chamber. So this will stay from 20 to 65 degrees, typically when we're running protein measurements, we run at, say, 20 degrees, so just a little bit below room temperature to prevent any excessive or any aggregation as the sample runs through them, through the columns. Now, just today in here, I'm running a single silica-based column for protein separations. So after the column, the sample moves down and out into the detector module, OMNISEC Reveal. So OMNISEC Reveal contains up to 4 different detectors. We start with refractive index, which is a universal concentration detector. We use that to measure just about everything that passes through the system. From there, we have a UV-vis detector for measuring, let's say, the concentration of anything with a chromophore. So proteins at 280 nanometers, DNA at 260 nanometers, or conjugated drug molecules maybe. Now, the detector is actually a UV-vis PDA. So it can measure from about 200 nanometers up to about 900 nanometers wavelength. So if you're looking at drug protein conjugates, for instance, where the 2 components are absorbing at different wavelengths, you can study both of those wavelengths together, which is pretty cool. After the UV-vis, we move to our light scattering detector, which is, of course, for measuring absolute molecular weight. So we use that to measure protein molecular weight, its oligomeric state, and to study aggregation. And then we move on to a viscometer, which a viscosity detector, we use it to measure molecular conformation and structure. From a protein perspective, actually, the most useful thing about it is its ability to measure hydrodynamic radius. So that's how we measure RH of our samples as well. So all those detectors are in series, and they're all housed within a single temperature-controlled compartment. So OMNISEC Reveal has actually got two doors at the front. The top just allows you to get to the UV bulbs for changing them when they need replacing. Inside the bottom compartment, as far as you can get in, is just to an inner panel where there are some user-exchangeable components, parts of the viscometer, the exchangeable bridge, and the delay column. Now, that whole compartment is temperature controlled, again from 20 to 65 degrees C. So typically I'm running at 20 degrees when we make protein measurements. And since we've got all the detectors in there together, it means that the detectors, the cells, the sample, the interdetector tubing are all kept at a constant temperature as the sample moves from detector to detector. So there's no variation in temperature as the sample moves from detector to tubing to detector and so on. The other advantage of that is it allows you to keep all the detectors very close together and minimize the interdetector tubing that takes the sample from detector to detector. And the reason that's a benefit is because as you move from detector to detector, you get a little bit of band broadening of dispersion. And by keeping the cells very close to each other, by minimizing the interdetector tubing, we can minimize that band broadening that occurs, and therefore maintain the resolution that we've tried so hard to get through our separation. We maintain that resolution, and then we get better analysis of the individual populations. So all those detectors are in series. The sample moves from detector to detector, then finally out to waste, actually through OMNISEC Resolve up to the yellow line and back to the waste bottle. So that's an overview of the OMNISEC system. Now what I want to do is actually take you through setting up some sample analysis or some sample measurements, and then after that we'll go on to analyze them and see what kind of information we can get.
So when we turn to the software, we actually start on this home screen, this start page, and this is just a bit of an informational page, so it gives us some quick links to some previously worked on data, some documentation such as the help and manuals, and then a brief update on the status of the system. So you can see we've got flow rate here, the pump pressure, and then the temperatures of the different compartments. Now, the first thing we should do when we want to make some measurements is check that our baselines are okay. So if I go to the Acquisition tab, then I already have a baseline monitor actually running. It's been going for a few minutes. And the system's well equilibrated, so we can see our baselines are nice and quiet and stable, and we're ready to run a measurement. In the detector channels you can see just a little bit of noise, and that's because we're zoomed in quite far on them at the moment. When the samples elute, we'll get a really good feel for the actual signal to noise. But they're all nice, low, smooth, stable at the moment, so we're ready to start making measurements. So I'll stop that, no need to save the data this time, and move over to the Sequence tab, and this is where we program our sample sequence. So I'm going to create a new sequence, and we'll give it a name, and this is protein demo 1. We're going to run just a handful of samples, so we'll start with BSA. That's our normal calibration and verification standard, good for checking everything's okay with the system. Now, sample type is proteins and aqueous, that is what it is. It contains the DNDC of the sample. Actually, we're measuring BSA, so I'm going to select that in particular, just because it contains information about the DADC, so the UV extinction coefficient for BSA. Our concentration is 2 mg per ml. We're going to do 100 microliter injections, and we're going to do 2 injections, and we're going to inject from the left tray, well A1. So our next injection is going to be an IgG sample, and this is just a protein sample, so we will select our protein sample type from the list, and there it is. So this concentration is also 2 mg per ml. The same again, we'll do 2 injections and the vial number has changed itself to A2. So our third injection is actually going to be a heated IgG sample, which we stimulated some aggregation. Again, concentration 2 mg per ml, this time vial number I3. And our fourth sample is going to be pepsin. So again, we select the sample type, 2 mg per ml, 100 microliter injections, 2 injections, and this time, well, A4. So that's our sequence set up and ready to go of just our 4 sets of samples, duplicate injections. Now, just to check on the run conditions, the run length is going to be 25 minutes. Our solvent buffer is just phosphate buffered saline. As with the sample types, we have a little database of different buffers and solvents that you can select from. And our column set is one of our PLS 3030 columns, which is a good high resolution column with low column shedding for good light scattering signals. And again, we have a database of these, which you can add to yourselves when you've got your own column sets, so you can store them by serial number, for instance, and then keep a record of what's been used on which column. So in the settings at the bottom, we've got a few things. Just turn off the UV lamp and turn off the laser at the end of the sequence to preserve their lifetimes. And then we can set the standby flow rate after the end of the sequence as well, just to preserve mobile phase. So let's say we're running overnight or over a weekend. The pump will slow down to preserve mobile phase until we're back in the office to check on the system. So we're ready to go. I'll just touch on the instrument controls quickly. If I bring in this tab on the side, you can see we're running at 1 ml per minute, and we can see we've got back pressure there. The autosampler has been primed and is ready to go. And our temperatures in our different compartments. The autosampler is running at 4 degrees, so we can put our samples in there and protect them from aggregation over time, overnight, if they're sitting there for a few hours. And our columns and detectors are just running at 20 degrees to keep them nice and stable, but actually below room temperature. The UV and the laser light, the laser are both on. Now, we looked at baselines and they were nice and steady and low, and our sequence is set up and our system is ready to go. So from here, we just click the start button, the sequence will be saved, and then the instrument will move on to acquisition and to starting the data collection. So it will move to the acquisition tab as it's just done automatically, and the first thing that's actually going to happen is the autosampler will go through a priming process, and you can see that in the bottom left there. It's telling you what's occurring with the initial wash before making the first injection. And this just ensures that the autosampler is fully primed, full of mobile phase, and is going to make nice, highly accurate injections from the very first one. So that takes a minute or two, and you can see on the video here what's going on with the needle as it washes itself and draws through some solvent. So once the autosampler priming has finished, you can see the message in the bottom has changed to waiting for injection trigger, and the autosampler is now going through the injection process, drawing up sample into the injection loop. When that's ready, we'll hear the noise of the valve turning to inject the sample, and the run will start. So there it goes, initializing data acquisition, and run starts to be acquired on the screen. Now I'm just going to change the axes to our auto scale feature, so we get a nice zoomed in view of our baselines to start with, and then that will scale as the run proceeds. So we'll let those measurements go, and while they're running at an accelerated rate in the background, I want to spend a few minutes just reminding ourselves as to how size exclusion works and what the different detectors are doing to give us a feel for the kind of information we can expect to get out of a measurement like this. So thinking about size exclusion theory then. Now, size exclusion, SEC, also known as GPC, gel permeation chromatography, is a subset of HPLC, but it's not an interaction affair at all. It relies on separation of molecules as they move through the column based on diffusion of the molecules, of the protein molecules, in and out of the pores of particles. And as they move through the column under an isocratic mobile phase, so the same continuous mobile phase, we should see a separation of our protein molecules according to their physical size. And the larger molecules come out first, elute first, while the smaller molecules elute later and later. So we should end up with a size-based separation of our different populations. And the way that works is that imagine a single gel particle within a column and a mixture of different molecules coming through. Now, as they move through the system, the molecules can diffuse in and out of the gel particles to different extents. The larger ones, like the triangle, are excluded from many and move faster. The squares get in a bit deeper, and the little spheres get in much deeper all the way to the center. And as the molecules move from particle to particle to particle, so the separation between them grows and grows and grows until our individual populations are separated. Now when the sample elutes, we're going to measure it with one or more detectors, and what we're doing with OMNISEC is measuring a whole range of different detectors to get as much information as possible. So our multi-detector SEC separation involves a standard kind of chromatography setup with degasser, pump, autosampler and column oven, and then the samples flow through a range of detectors, starting with refractive index, moving through to a UV-vis PDA, a light scattering detector, and an intrinsic viscometer. So let's start with refractive index. We all know that when we dissolve something into a liquid, it changes the refractive index of the solution, the way the light bends as it passes through. And this response is directly related to concentration, so we can use the RI detector as a very sensitive concentration detector for just about any sample we want to measure. The next detector in the sequence is a UV-vis PDA, which of course we use to measure UV absorbance of anything with a chromophore, and obviously proteins are very strong UV absorbers, so we can use this as a second concentration detector. We typically use RI as the primary one because it removes any questions of molar extinction coefficients and UV absorbance differences between samples, but it's nice to have both because there are occasions where you want to measure conjugates, for instance, so a protein conjugated with polysaccharides or a PEG or membrane protein detergent from a membrane protein application. And so two concentration detectors with the RI and the UV. The next detector is a light scattering detector, which of course we use to measure molecular weight. So when you shine a laser on your molecule of interest, it scatters light, and that light scattering intensity is directly related to the molar mass, the molecular weight of the sample, according to the Rayleigh equation. And so by using a light scattering detector, we can directly measure the absolute molecular weight of our protein, regardless of its structure or where it elutes from the column, anything like that. We get a direct and accurate molecular weight measurement. So the final detector is a viscometer, which is a measurement of molecular structure. And just to keep this nice and simple, it's the inverse of molecular density. So we imagine a protein being a very high density, in most cases, globular compact molecule, and a high density is a low intrinsic viscosity. On the other hand, a more extended, open, fibrous molecule will have a higher intrinsic viscosity and a lower density. So a viscometer is a way to differentiate the two molecules in the image there, that sphere and the string of spaghetti, if they're the same molecular weight. So the light scattering would see the same molecular weight, but we can use viscosity to distinguish structures. And I'll show you how that can relate to proteins and protein aggregates right at the very end of the presentation. So just to summarize that then, what are we doing? We have light scattering detectors, refractive index, UV absorbance detectors, and a viscosity detector, and those are the signals that we're measuring. We combine those, in the case of the concentration detectors, to maybe measure a bit of compositional information, such as with proteins and PEG conjugates, and we can use those to measure the sample concentration. Sample concentration combined with light scattering intensity gives us molecular weight, which is the thing we're most interested in, and to a lesser extent for proteins because they're generally too small to measure, but the radius of gyration as well. Maybe that comes into play with some very large aggregates. And then on the other side, combine concentration with viscosity, and you can measure this property of intrinsic viscosity, this measure of density. But more interesting maybe than intrinsic viscosity is that you can combine that with molecular weight to calculate hydrodynamic radius as well. So by combining the two, we can actually get a physical size measurement. And all of these parameters and measurements come out of that one single SEC run. Okay, so when the data collection is finished, we can see our sequence complete message in the bottom left there, and our data has been saved in the database. So I click Open Data, and then all of our data is stored in this database, and you can see you can select any combination of sequences, samples, and injections. And so I'm going to select the entire sequence, and then load that into the analysis view. Now once the data is loaded, you can see the list of samples, list of injections on the left there in the order we ran them, our raw data chromatogram in the middle, and where our results will appear on the right. Now this view is nice and customizable actually. You can maximize the individual squares and customize this table to display the the information you want. And likewise the same with these windows, which you can maximize to look at a slightly simpler interface. And any individual window you can change to display different data. So for instance, we'll go and look at overlays in a little while. When manipulating these graphs, we can zoom in by drawing a box around the sample, or in fact we can scroll and zoom in on any of the individual axes. So we can really format the view here to look however we like. Now I already have a calibration method created and ready to go. So I've taken care of all the detector offsets, the band broadening corrections, and the detector constants, and we're ready to go and start analyzing samples. But I like to run something like BSA as a verification that everything is working okay and as expected. So the first thing we're going to do quickly is analyze our BSA and see that we get results we might expect. So I need to set some baselines and limits, and I can do that with the controls up here. For instance, I just click Set Baselines on all axes, and then I can come and select my start and finish points. And when I let go, the software will draw baselines across all the different detectors. I'll zoom in for selecting the individual peaks and maximize that to give me the best view, and then I will do that for the individual peaks as well. So we'll just select the I'm actually going to select 4. These 3 peaks are quite well resolved, and then this 4th one I'm just going to take all these aggregates and treat them as one individual peak. Now the software's been analyzing in the background every time I put a peak down, and you can see the results here. On the derived data we see where our molecular weight trace cuts across the refractive index chromatogram. If I zoom in a bit, then we can see really beautiful stable molecular weights across the monomer, dimer and trimer peaks, indicating that these are nice pure monodisperse populations. And then in that last long one, the aggregate peak, we've just got a broad range of molecular weights stretching up into millions and above. And that data is, the numerical results are presented in this table down here. So you can see we've got a measured molecular weight of 66 kilodaltons for the monomer, 134 for the dimer, 205 for the trimer. So all of these are exactly where we would expect them to be for our BSA monomer, dimer, trimer. Our MW over MN value is polydispersity, and a value close to 1 indicates that these peaks are absolutely pure. So these tell us that these are monomer, dimer and pure trimer in those peaks. The 4th peak has a higher molecular weight and a wider range of molecular weights as indicated by that MW over MN number there. And this tells us this is a broad range of poorly resolved aggregates. We can also look at intrinsic viscosity, which is a measure of structure, and that gives us hydrodynamic radius, which is what we're more likely to be interested in. So we can see our monomer peak, 3.5 nanometers, 4.9 for the dimer, 5.9 for the trimer, and then 8 and up, in fact, for the aggregates. It tells us that our fraction of samples, our monomer is about 75% of the sample, 15% dimer, 5 trimer, and then about 5% of those larger aggregates. And then we have our measured recovery and concentration there as well. The recovery is not quite 100%, and that's just because I've cut off the bottom corners of these peaks, so it's just a little bit not taken into account. But overall, you can see we've got a really nice, comprehensive characterization of our BSA, and our results are really nice and accurate. So I'm going to move on and analyze a couple of IgG samples, and then we'll look at the heated IgG as well. So I just click on the next IgG. Do I want to save my results? Yes, so that I can come back to them later. And after a second, we move on to our IgG sample. It looks very similar, with some primary peaks and then some aggregates. There are actually shortcut keys for setting in baselines and limits, so I'm going to use those. And again, I'm going to call all the aggregates together. Then the second peak. Then the third peak. And again, in our molecular weights, 2 really nice monodispersed stable populations, and then the aggregates more varied in their molecular weight and higher up. So you can see I've got about 145, 150 kilodaltons for the IgG monomer, 300 kilodaltons immediately identifies the other one as a dimer, making up about 90 and 9% of the sample, respectively. And then just a couple of percent, just 1% in fact, of these higher molecular weight aggregates, which are in fact up at 2 million or more. So very high molecular weight aggregates in there. Size-wise, measuring 5 nanometers for the IgG monomer and about 7.5 for the dimer. Again, perfect measurement of the RH there. So what I'm going to do is run through a couple of these, keep going with a few more of these samples. So we'll save those results and move on. And again, set baselines. Zoom into the sample and analyze those peaks. Now I'm not quite happy with my intrinsic viscosity baseline there, so I'm just going to drop that down a bit. I can pick up any one of these baseline points and move it to wherever I please, so obviously we can make it go silly, or I can just lower it down a bit more to what I think is a more appropriate baseline value there. And again, very similar results there, so let's move on to our heated IgG sample. Now this, you can see, looks quite different. There's this third very large peak in the light scattering, and of course we know this is going to be some more aggregates that we've created by heating up our sample. So I'm going to go through the same routine though, just to keep everything consistent. And again, 3 nice peaks, stable molecular weights, and then increasing in the aggregates. A couple of things to note: our dimer molecular weight is actually slightly higher now, and that's because these aggregates are starting to dominate and they're not well resolved from the dimer peak. So a little bit of an increase there, but that's not a problem. The aggregate molecular weight, actually around 2 million, is not changed too much. It's actually a slight decrease from what we were looking at before, but of course the fraction of sample is much higher. These are now nearly 5% of the sample instead of being just 1% as they were previously. So then the fourth and final IgG, we'll set baselines and limits over those again. And pretty similar results, so very nice. Now once I've saved those, what I want to show is how we can compare samples and overlay them and really get a feel for how the IgG sample has changed. So I'm going to maximize this view and I'm going to change it to the overlay view. And then just by selecting multiple injections in the record view there, I can bring in all those injections into a single chromatogram. I'll baseline subtract them, so we're looking at the kind of them all overlaid very nicely, and here we can very nicely see the difference. If I zoom in here, we're looking at the RI trace here, by the way, and you can see in the red and purple sample, the initial sample, we had our monomer and dimer, and then just a small amount of larger aggregates. But then in the black and green, the heated sample, you can see we've got this growing population of aggregates there. If I switch to the RALS detector, the light scattering detector, then you can see that difference very dramatically in the presence of those large aggregates, which of course scatter so much light. So we get a very nice visual representation, both of the precision, the repeatability of the couple of duplicate injections, which are nice and consistent, and then the difference between the raw and the heated samples. So it's a really nice, quick way to compare samples. Now, additionally, the results table has been updated to incorporate all the data from those samples. So I'll run through that. If we just selected the one, then we just have our peaks 1, 2, and 3 for our one injection. If I select the two IgG samples, then you can see this table updates, and now we can see 145 kilodaltons for both, just about 300 kilodaltons for both, and then 2.5–2.75 million daltons for the aggregates. And in fact, the software will calculate statistics for both of these automatically. So we can see we've got just for the monomer and the dimer molecular weights, just a couple of percent or less, in fact, in the monomer case, of variation there. A little bit more in the aggregates. They're going to be a bit more variable because of their small amounts really within the sample. And so we can see that for the molecular weight, we can see that for the intrinsic viscosity, and for the RH, which again, just a few percent variation in there, telling us that we've got really nice repeatable results between those samples. Of course, if I add in the two heated injections, then we can see any additional variability that might be coming in. For instance, the aggregate molecular weight is becoming a bit more variable, and also the fraction of sample, we can see that it's gone up from 1 to 2% in the initial samples to about 5% in the aggregated samples. So very significant differences and very easy to visualize and see. Of course, these tables can be copied out to another software package, and they're fully customizable as well, so you can just look at the information you want. So the last thing I want to do is analyze these couple of pepsin samples and compare those to the IgG. So I'll quickly, as before, set some baselines and limits. And you can see that for the multiple samples, this can be done so quickly. Just flicking between samples, setting baselines and limits, and then immediately analyzing them. So in our pepsin here, actually the center peak is our monomer, about 38 kilodaltons, very close to the expected molecular weight. And then we've got some degradation products, a lower molecular weight, and some aggregates at high molecular weight. And I will do the last sample as well, and then we will compare this with the aggregated IgG samples. And there we go. Again, monomer, degradation products, and the aggregates. So what I want to do now is overlay those samples briefly and compare the intrinsic viscosity signals for them. If I go to the overlay view, so this is our RI. If I look at the viscometer signal, And you can see the viscometer signal for the aggregates in the pepsin, and indeed the monomer, is far, far higher than the IgG. And that's because these proteins have different structures to each other. Now, if we look at the numerical data, and we're only interested in peak 1s here. So peak 1 for the heated IgG has a viscosity of about 0.15 and a size of 16 nanometers for about a 2 megadalton aggregate. Likewise, 2 megadaltons for the second one, and 16 nanometers, 0.15. So really nice repeats there. Now the pepsin aggregates are about 2.2 megadaltons as well. So they're similar molecular weight, but their intrinsic viscosity is 1.4, 1.5. So it's 10 times higher than that of the IgG. And that feeds into a hydrodynamic radius of 40 nanometers, 39, 40 nanometers in size compared to the 16 nanometers of the IgG. So what this tells us is there are big differences in the structures of our aggregates between the pepsin and the IgG. The IgG is a much more compact globular structure, whereas the pepsin is a much more extended and open structure, possibly a fibrous aggregate, something like that. So not only can we characterize fully the samples for their different populations and the molecular weights of those populations, but we can also investigate their aggregation state, the molecular weight of the aggregates, and also then even to some extent the structure of the aggregates. So a very nice demonstration of kind of all of the data that you can get out of the system there.
So that's pretty much everything I wanted to talk about today. I hope it's been a useful introduction to the product and to what we can do with it. Just to summarize everything we've spoken about. So OMNISEC is our complete advanced size exclusion chromatography system. OMNISEC Resolve, the module on the left, is our degasser, pump, autosampler and column oven, and that takes care of the chromatography side of things. The module on the right, OMNISEC Reveal, houses all of the detectors together, the refractive index, UV vis, light scattering and viscometer. Now, OMNISEC Reveal is customizable, so if there's a particular combination of detectors you're looking for, just refractive index and light scattering maybe, to focus on absolute molecular weight, then that's totally possible. OMNISEC Reveal can also be added to an existing chromatography system. So let's say you've already got a single detector system set up somewhere and you want to bring light scattering to add some absolute measurements, then we can add that onto the existing system and they can work together. In the software, that takes care of the sequence setup and the acquisition. We can calibrate the system, and then we've seen how we run through the sample analysis for different proteins to measure all sorts of parameters, their molecular weight, oligomeric state, hydrodynamic radius. We've seen how we can look at repeat injections to study the statistics of them to get a feel for the repeatability. And we've looked at how we can compare different samples to see how maybe they're aggregating differently, how they've assumed a different oligomeric state, or whatever, to compare differences between them. And that's all done very nicely in some nice, really quite intuitive software. So, as I said, I hope that's been a very interesting introduction to the product and to its capabilities as well. And obviously, if you've got any questions, please don't hesitate to get in touch. Thank you.
Thank you for listening. For more information, please visit www.malvern.com.